Okay, welcome to another live session. The floor is open for your questions on astronomy. It's been a while since we've done this. We'll try to keep it up through the summer, every few weeks. Floor is open.
So our first question is from Maureen, and she asks, so dark matter has a mass, but has no interactions with EM radiations. Could it be correct to think that of it as a black body, its temperature approaching the absolute zero, regarding Planck's law?
That's an interesting question. So we should just back up and say what we understand the properties of dark matter to be. So that, as the question implies, we think the last plausible candidate for dark matter, having ruled out larger objects, is a subatomic fundamental particle. And since it's hypothesized, since obviously dark matter is dark, it neither emits nor absorbs nor really interacts with electromagnetic radiation. So its coupling to the electromagnetic force is weak. That's what we understand. It has to be ubiquitous, and it also has to be a fairly massive particle, since it outweighs normal matter, which is the sum of all protons and neutrons, by a factor of 6. As for its temperature, or equivalent temperature, it's a good question. Its temperature, of course, in practice, because it's a particle, will depend on its energy and its velocity. And the two main distinctions of the types of dark matter, fundamentally, are whether it is so-called cold dark matter or warm or hot dark matter. And the phrase warm or hot refers to the speed of these particles at the time they were released to travel freely after the microwave background radiation was created a few 100,000 years after the Big Bang. If the dark matter is cold, which we do believe is the fundamental nature of dark matter, then it will be subrelativistic at the present day. So these are massive subatomic fundamental particles traveling at high speeds, but not relativistic speeds, through the voids of space. And their aggregate gravitational interaction is sufficient to hold galaxies together and to cause large-scale structures to form in various ways. So the temperature of the particle, or the matter rather, really depends on its local energy. And it isn't actually super cold in that sense. So the simple answer to the question is no, dark matter does not have a low equivalent thermal temperature. It has a high temperature.
Okay, and our next question is from John, kind of a related question. Would E equals mc squared apply if black holes were turning matter and energy into dark matter and dark energy? Is there a way to tell if dark matter or dark energy is increasing or decreasing in size or volume?
So as far as the black hole part of the question goes, the nature of an event horizon at the boundary, so-called, to the black hole is that it's an information membrane. Nothing can get out or only can go in. So essentially we are ignorant of anything happening inside the black hole. So whether matter is being converted into energy backwards and forwards, essentially we don't know, and we may never know. At the edge of the black hole and beyond the black hole, as E equals mc squared implies, there is an interconversion between mass and energy in the form of either particles and antiparticles being created and going out of existence, or those particles and antiparticles disappearing into pure energy. So that equivalence is observed in the lab and also in the universe as a whole. But dark matter doesn't seem to play a particular role in that. Of course, in principle, the dark matter fundamental particle has its own antiparticle. But just as with all the other particles in the universe, neutrons, protons, electrons, or quarks, the anti-component, the antimatter component of those particles is extremely rare. And that asymmetry is built into nature in a very profound way.
Okay, and our next question is from Nicola. And he asks, Professor Impey, is it worth buying a telescope? Compared to the telescopes that researchers use, there's nothing new our own telescopes can show or teach us. I can just go find pictures online or find a live telescope and observe it from my computer. Also, the light pollution is big where I live, so I can't really go to my backyard to watch the sky. I would have to travel about 7 kilometers to get to a clear sky. So again, I ask, is it worth it to buy a telescope?
Well, that's a good question. I mean, my answer would always be yes, it is, for a couple of reasons. If you're interested in astronomy, if you're interested in astronomy to study a MOOC or take a MOOC, then you clearly are more interested than the average person. And one way to fuel that interest is to get familiar with the night sky. The reason why it's still maybe worth doing, even if you can't see a need for a telescope and you live in a slightly bright place, is that telescopes have really improved a lot. and they're cheaper. So you get much more bang for your buck than you used to 10 or 20 years ago. There are additional vendors in the market. They're using lightweight materials, but not low-quality materials. So for a couple of $100, you can get more than an entry-level telescope. And also, you've saved yourself the trouble of learning the sky, because these are sort of they're called go-to telescopes, which essentially means once you've aligned them, which is a fairly simple procedure, you can just tap from a list or attach to a computer, use a web browser to send the telescope to a part of the sky or a particular object, and it'll point to that object. So that makes the observing easy. So you've got a cheaper piece of hardware than it used to be. You've got ease of pointing and finding things in the sky. And actually, even in a suburb, you can see reasonably dark sky objects. I agree, if you were in a real city, you'd have trouble. But if you only have to go 7 kilometers, 5 or 6 miles to get a dark sky, that's probably worth it, because you can set up that telescope fairly easily. And on a nice warm summer night, it's not even uncomfortable to be outside. So I would suggest that, yeah, it is worth it having a telescope. And once you've started observing the sky with a telescope that's easy to use and of reasonable quality, you'll find you're seeing some pretty interesting things. For example, with these couple $100 telescopes from a reasonably dark location, you can see more than a handful of galaxies, several dozen galaxies, extending out to distances of 50 or 60 million light years. And that's pretty amazing, to be able to see light that's been traveling since far longer than humans have been human, almost back to the time of the death of the dinosaurs. So that's pretty remarkable that you can do that with a small piece of hardware. So maybe that's not a compelling argument, but I would say you should investigate it. And if you get a telescope, especially if you know some young people, if you have kids of your own, or know kids that might get interested in the subject through observing with a telescope, that's sort of the entry-level way of learning about astronomy as a young person. So I would recommend you look into a telescope.
Okay, and our next question is from Scott. Could the moon have come from Mars? I've heard some think it came from the Earth after some kind of collision or breakoff. If this could have happened, is it possible that the same thing could have happened there, that is at Mars, and ended up here? Or do they have geological proof it could not have come from there?
Interesting question. So you're alluding to the fact that catastrophes or violent collisions were a part of the history of the early solar system. And we've got pretty good indirect and even some direct evidence that that happened. The hypothesis that the moon splashed off the Earth roughly 50 million years after the Earth formed, so very early in the history of the solar system, is a pretty good hypothesis, substantiated mostly by the lunar rocks brought back by Apollo. So that's very direct geological evidence supporting the idea of an impact with a Mars-like object, but not Mars, that splashed off the moon. And there were about 1,000 what are called planetesimals, that is 1,000 large asteroid-sized objects that would eventually collide. A lot of them smashed into smithereens, and a number of them accreted or merged to form the 8 major planets of the solar system. We think it's not Mars that did this or that traveled to the Earth's position, because the Martian geology is quite different from lunar geology and terrestrial geology. The moon and the Earth have very similar geology that we can prove with the rocks we've brought back. We do have Martian meteorites that have come to the Earth, about 50 or 60 of them, so we have enough Martian geology to compare to terrestrial geology, and the geology is really quite different. So Mars rocks are quite unique and distinguishable. So I think Mars has always been where it is, and the Earth has always been where it is, and there hasn't been transfer of much between them except for a few rocks that we've got falling to Earth, which are obviously representatives of a fair amount of debris that travels through the inner solar system.
Next question is from George, and he asks, which came first, the black hole right in the center of our galaxy, or the galaxy itself?
Well, that's a great question, and it actually connects to my research area, which is the evolution, the co-evolution of galaxies and supermassive black holes. So in my research, I use large telescopes, our large telescopes, and sometimes a Hubble, to look at how galaxies and black holes have evolved together in the universe, trying to look at large samples of them and trying to follow this history or this story over most of cosmic time. And so the Milky Way is, of course, our most proximate example of a black hole, a big black hole, 4 million solar masses, and it's a galaxy we live in, so we can see it up close. And it's a fascinating question. Did black holes or galaxies come first. The general belief is that the galaxy started to form from small pieces. Our galaxy is the subject of a history of mergers of perhaps thousands of smaller galaxies over a long period of time. Much of that merging happened early on, and only a few late examples are being seen right now as we speak. And that within that forming galaxy, but pretty much after it had formed, you would have the initial black hole. So in the center of the forming galaxy, you might have a black hole that's roughly 1,000 or maybe a few thousand times the mass of the sun. And as the galaxy evolves, that black hole can grow quite happily and quickly because there's a lot of gas available in the early universe. The galaxy is still forming from mergers, so there's a lot of new gas and stars being added to the center. And so the black hole grows quite quickly. And then at some point, it stops growing as much because the galaxy is mature, and also because there's less material falling in from outside as the expanding universe sort of thins out the material between galaxies. So we think the galaxy did form first. It very quickly had what we'll call a seed black hole of only a few thousand solar masses. That black hole grew fairly quickly, in the case of the Milky Way, up to a few 100,000 solar masses, and then more slowly and steadily up to its present 4 million times the mass of the sun. And over the last 4 or 5 billion years, that black hole hasn't really been growing very quickly at all, and it hasn't been very active at all. And currently, the black hole in the center of our galaxy is in a non-active phase. Even though there is a fair amount of gas and dust nearby, it's not devouring material. It doesn't have a luminous, bright accretion disk and relativistic jets that are pumping out huge amounts of electromagnetic energy. If it did, if it was like a quasar, given that it's only 27,000 light years away, the center of our galaxy would be visible in the daytime sky, almost comparable in brightness to the sun, which would be remarkable. But since it's a quiet black hole, the center of our galaxy is a faint object. It's invisible, and mostly, of course, you'd have to be in the southern hemisphere to see it. But it's a good question.
All right, and our next question is from Heike. And she asks, if I consider light as a particle with a mass that can be calculated, it cannot escape from a black hole for reasons of gravity. So if one would be inside a black hole, is the black hole inside itself then bright because of the light that's within it? Or does the black hole stop the light then, being fallen into the black hole? Its behavior as an electromagnetic wave, so the black hole appears from an interior view as also black.
Well, that's a good question. I mean, it's actually very difficult to answer, even theoretically, and impossible to answer observationally, because we've never been inside a black hole. The question of what's the physical state of matter inside a black hole and how radiation and matter behave inside a black hole is, of course, an intensely interesting subject, and it's really a theoretical subject. As I say, you'll never be able to do the experiment at any time soon. But the best idea, it depends on the black hole, is the truth. If it's a stellar mass black hole, the kind of black hole left behind when a massive star dies, the gravity is, of course, extremely intense. The event horizon defining the region from within which light cannot escape. However, within the black hole, in principle, radiation can travel and is mixed in with the matter. So it's not that the black hole inside, once you're inside it, is actually necessarily going to be dark. It's also presumably possible to travel within the event horizon of a black hole. The density is high, but it's not infinite. It's probably a plasma. It's probably a physical situation where travel is possible if you had a means to do it. And the more massive the black hole, the more that is true, because the density of a black hole actually goes down as the mass of the black hole goes up, which is an interesting fact. The massive black holes at the center of quasars have densities inside their event horizons no denser than water. So it's not even a very extreme state of matter. So I think the answer is, theoretically, yes, light can travel within the black hole. It is, however, bounded by the event horizon, which is an information barrier. So no radiation nor matter can escape that region. It is essentially trapped. And you can think of the space-time as being so warped that radiation is essentially going around in circles or completely trapped, as would any object or particle inside the event horizon.
Great, and our next question is related from Ayush, and hopefully I can make sense of this. So, as per the theory and observations made till now, Anything that enters the event horizon of a black hole never comes out. Consider this scenario. What if electromagnetic radiation or energy keeps entering a black hole over a large period of time, eventually providing enough energy to the matter inside to expand against its own gravitational force, making it thinner over time and leading to reconversion of a black hole into normal space? Once that happens, a blast of trapped energy would be expelled out. Is such a situation theoretically possible?
It's an interesting question. I've sort of partially answered it with the last question. As a black hole consumes mass and grows, that's a fairly well understood process. That mass or radiation, if it's radiation that's entering the event horizon, is indeed lost from the visible universe, sealed off within the event horizon. But the thing you're talking about, the speculation of a burst of energy leaving the black hole, I don't think ever happens in the theory, because the event horizon continues to be defined, it's really how it's defined, as an information barrier, a membrane from which no matter or radiation can escape. So as more and more mass or energy or radiation falls into the black hole grows. It grows in mass and it grows in size in such a way, as I mentioned a few minutes ago, that the density of matter and radiation within the black hole, within the event horizon, goes down. And so the state of matter, if you like, gets less bizarre because the density is going down. But there's no part of the theory that suggests that at any point that matter or radiation erupts back into the regular universe or escapes this information membrane, because the definition of the event horizon is a barrier to information. That's how we understand a black hole. So basically within the theory, what you're asking cannot happen.
All right, and our next question is from Dimitri, and he asks, Professor Impey, do you accept the theory of the multiverse?
Well, the multiverse theory is highly speculative. It's at the frothy edge, if you like, of the subject of cosmology. So very briefly to encapsulate that idea. The idea of the multiverse emerges from the situation of the very early universe, the Big Bang, where at some point, very early, at first tiny fractions of a second, the entire universe that we see as 46 billion light years in every direction, containing 100 billion galaxies, was smaller than a proton. And at some point, the genesis idea in cosmology, the Big Bang, the initiation event, is a quantum fluctuation or quantum event. That becomes the sort of theoretical construct out of which you could hypothesize there might have been other quantum fluctuations. So you recognize that immediately we're talking about both what caused the Big Bang and what the precursor state was. And to be correct, it's the Big Bang theory or model is just a physical description of what happens from a state of near infinite temperature and density. So if we're being strict in our scientific method, the Big Bang model only describes what happens after that initial state. It does not make a prediction or a description of the precursor state, if there even was one, or if that's even a meaningful statement. So the multiverse idea is therefore really speculation. It has no affirmation. The idea of other potential parallel universes with different physical properties that emerge from this precursor or substrate state from which our universe emerged as one large event. People who work on the multiverse theory insist that it has some legitimacy, that it's worth talking about. It's not a completely ludicrous idea, but it's based on physics that we don't really understand, because you have to have some grand unified theory of the four forces of nature, which is to say a quantum gravity theory, before you can even understand this precursor state. So we don't have a physical theory with which to make predictions of multiverse models that are very rigorous. So that's a second critique against the multiverse model. The first is that you're going beyond the bounds of the Big Bang explanation. And the second is that you don't have a physical theory to understand this state, because we have no quantum gravity theory. People talk about string theory and all sorts of things, but those are untested theories too. So you can't take two untested things and put them together and say that you understand the precursor state of the universe. So I would say to most practitioners, multiverse theory is pretty extreme speculation. It's not in the realm of testable science yet. People who work on it and are optimistic about it are trying very hard to make it a testable idea. And at that point, it will enter the realm of science, and we can test the idea, but we're not there yet.
Okay, and our next question is from Nazar, and he asks, Professor Impey, it's another personal question, how did your interest in astronomy start?
Well, I got into astronomy through physics, and most of my colleagues get to astronomy by one of two paths. They are kids who had telescopes when they were small and got intrigued by the sky and were hands-on astronomers living in places where they could see the sky, and they traded up their telescopes for bigger and bigger telescopes. So they're practitioners. You still have to study science at college, of course, and usually physics is the first degree for most professional astronomers. In my case, I grew up in cities, New York, London, places like that, where there was no dark sky and not even one very close by. So I never had a telescope growing up, and I never lived in a place, even near a place where I could use one. So I got into astronomy through physics, which is the standard path in terms of a first degree anyway. You subsequently do a PhD in astronomy. And I was in London doing a PhD, a bachelor's in physics, and then moved to Edinburgh to do a PhD. And that's a normal path. I learned to use telescopes, fairly late on as a teenager, in fact, before I lived in a place and I never actually had my own really good telescope. I'd borrow other people's or use the ones at our local observatory. But by the time I was an undergrad, I'd started to go on observing trips and get interested in the subject and think I might want to do a PhD in it. And I started to visit some beautiful dark sky observatories. In fact, I came to Arizona, the place I currently work, in my first year of graduate school, just on a visit, just for a single observing trip with my supervisor. And I recognized what an amazing place it was to do astronomy. And some years later, after finishing a PhD and 2 postdocs, I ended up back here for my faculty job. Never left since, because we have wonderful skies, and we have telescopes in Chile. So if the skies aren't quite dark enough in Arizona, I can always go to South America for the darkest skies possible.
This question is from Doug. Can you describe the day in the life of a professional astronomer? Does an astronomer have autonomy to do his or her own research?
Yeah, it's a good question about the profession. There may not be a single, archetypal astronomer life, so I'll just take one example and maybe mention a second. So most astronomers are academics. They work in universities and colleges like I do. And the second largest set of astronomers work in national observatories or national labs or private institutions like the Smithsonian or Carnegie Institution that have astronomers working there and have facilities for astronomers to use. So most astronomers live a professional life where they're combining research and teaching, and that's my life too. In my case, I'm an administrator too, so I'm trying to balance 3 things. So a typical day in the life of a professional astronomer, ironically, may not involve observing through a telescope. If you're an amateur astronomer, you probably want to be out there every dark night. And if you're growing up and have a telescope in your backyard and live in a nice place, you might be using it almost every night. But professional astronomers are using telescopes where the time is hard to get, and where the bigger the telescope, the less time you get. If you're a good astronomer trying to get time on a major facility, you may only get 4 or 6 nights a year on a 6, 8, or 10-meter telescope. That's not very much. So typically you might have 2 observing runs of 2 to 4 nights each, separated by a few months, scheduled way ahead of time, where if the weather just turns out to be bad, you're out of luck and have to wait till the next time. So professional astronomers are not observing all the time, which is probably a standard misleading impression that you might have. A lot of the data is valuable. That hard-won data that you only spend some nights a year getting takes a lot of time to reduce and understand and analyze. So for every night you're observing, you're probably spending several weeks reducing data, analyzing it, extracting information from it, and then several months turning those results through further analysis and maybe some computer modeling into a published paper. So the standard path of a professional astronomer who's doing observation is to use some hard-won and kind of sparse telescope time with big facilities to feed into a research project and then publish the results of that research. And that's the cycle. And that whole cycle, from applying for the telescope time to finishing the paper and publishing it, could take 2 years. It's probably a typical time for the whole cycle. If you're a theorist, your cycle is a little more rapid because you're not depending on data. You're working out of your head or perhaps with a computer to do some interesting analysis in a more theoretical way. Now you'll relate it to data, but that data is probably readily available, so you don't have to go and get it for yourself. So theorists can be a little more nimble, and their cycle, if you like, from original idea to paper Could be quicker, maybe only a few months or 6 months. So astronomers are doing that for their research, and for a typical faculty member at a major university, like the University of Arizona, about 30 or 40% of your time and your workload is on research. A similar amount will be on teaching. And so you're probably teaching a class, perhaps to graduate students, perhaps to undergrads, and perhaps to non-science majors. I just finished teaching a class of 150 non-science majors taking introductory astronomy. So that's my teaching for this semester, and it's kept me fairly busy. But astronomers teach at different levels. And then the third component of a professional astronomer's life in a university is service, which is service to the university. You have to sit on committees and exams for other students, sometimes in other departments. You have service to the profession, where you maybe serve, as I've done on Hubble Space Telescope time allocation committees, or for the national observatories. You review post-op applications, or just do various things for the community that you don't get paid for. They're just expectations of astronomers to help out, basically, to make the profession run better. And that's the last and maybe the smallest component of your workload. So astronomers are typically balancing those three things. If they work in the national lab situation or the National Observatory or one of these research institutions like Smithsonian and Carnegie, then the teaching part is missing because those are not teaching institutions. So in a sense, they're in a luckier situation. They get more of their time for research. They probably have to do a little service or admin, but those are more research pure institutions. But for those of us like me who like teaching, that would not necessarily be a better situation. I like where I am.
Okay, and our next question is from Kanish. He asks, says that currently I'm in 11th grade and like to work with NASA and go to space. I've read multiple books about the subject, Arthur and Clarke, Stephen Hawking, Mikio Kaku. But he'd like to ask you, Professor B, how should he go about his dream, working for NASA and being an astronaut?
Well, it's a good dream to have. I mean, there are not many astronauts, so that may be a challenge. However, the private space sector is opening up as we speak, and if you're just young and still in school and about to go out in the world, you'll probably be living in a time when you could be an astronaut without working for NASA. That's actually an important point because NASA doesn't really hire many astronauts. But you can still get your feet wet. I would suggest that when you're in your studies, and presumably if you want to set your course towards astronomy, when you leave high school, you'll have taken enough math and physics that you're either going to be studying math, physics, and or astronomy as an undergraduate. And almost as soon as you leave school, and sometimes even before, there are various internships possible that are through NASA. So if you want to get the NASA experience, you can start doing that at college. NASA runs a program called the Space Grant Program, and they have this program in every one of the 50 states. We have a program on campus, and so to take us as an example, every year something like 40 or 50 undergraduates, often freshmen, so it can happen in your first year at college, do an internship paid for by NASA working on a space science or planetary science or astronomy related subject for maybe 10 or 15 hours a week. It's a way to get your feet wet in research. And of course you're working on the NASA program, so you have connections to NASA, and it will obviously look good on your resume because it will say you were a NASA Space Grant intern. So that's a very particular example that happens all around the country. Now, you can also apply to programs where in the summers, when you're not taking classes, you can actually work in a NASA center. So each of the major NASA centers, not headquarters, I don't think, but Johnson, Kennedy, JPL, Goddard, all the major NASA centers spread around the country have internship programs for students. Some of them have them for high school students, but probably not most. But they all have internship programs for undergrads in different ways, in different forms. Some are more technical, like engineering, and others are more science-based. So you just have to search those NASA websites for those internship opportunities at the NASA centers, and you may be able to work there too. Now, none of those are direct pathways into being an astronaut because the astronaut program is run at a Johnson Space Center, and you can search their website, and there's this very clear process outlined in the astronaut section of the Johnson Space Center website where you apply to the astronaut program. And of course, it's a highly selective, low probability of being accepted. Every time they have an intake or an application cycle, they probably get 50,000 applicants, and they winnow them down and probably accept a few dozen into the astronaut corps, of whom many may not ever fly. So I don't want to discourage you, but it's worth being realistic about what the odds of being a NASA astronaut are. But as I mentioned, I think within a decade, there are going to be other ways to get into space through the private sector, and they may end up being many more ways to get into space outside of NASA than inside of NASA in the future.
Okay, the next question is from Gabrielle. The universe is depressingly large, even if we could travel at light speed. Is there any other theoretical research ways to overcome this problem?
Well, it is large. I don't know if it's depressingly large. It's the existential angst of living in a large universe. It's something that people have to wrestle with in their own way. But it is a fundamental problem, the one you allude to. The time travel issue, because of the finite speed of light, is a huge issue. And it's an obstacle, forget about the universe itself, it's just an obstacle for us ever traveling to the stars, because at even without violating the laws of physics, traveling at 1/10 light speed, there's no law against that, it takes a lot of energy, but it could happen, means you're talking about 2 generations to get to the nearest star, 2 human generations. So that really just tells you how big space is. And compared to that, the distance to the center of the galaxy or to the nearby galaxies, which are millions of light years, at a 10th light speed, you're talking about tens of millions of years. It's just ridiculous. It's just not going to happen. So it's natural to wonder if there's a way to violate that, essentially a way to do warp speed. Now, warp speed and warp drive and those science fictional Star Trek type concepts, there are science fiction. There's no physical basis for believing we'll ever be able to travel faster than light. Relativity postulates that the speed of light is an ultimate physical limit, and everything in the lab has affirmed special relativity for over a century. So that's a pretty hard call to imagine that relativity is wrong and you can actually go faster than light. We've seen no sign of it. The other escape clause people try to use is the fact that space-time might not be simple and linear and might be multiply connected. There may be places where space-time somewhere connects to space-time somewhere else, and so you can bypass the length of time and difficulty of traveling through the voids of space because the space-time curves over on itself and lets you take a shortcut, essentially. We've seen, and black holes and white holes are the sort of science fictional concept of that. We've seen no evidence for white holes. We've seen no evidence that space-times are connected with wormholes or that there are ways to tunnel instantaneously, essentially, from one region of the universe to another. So unfortunately, that's not really a real prospect, too. I think with what we know and with the laws of physics as they stand, we are kind of trapped in our local region of the universe. We may someday travel to the stars, I hope we do, but it is very unlikely that humans or any living creatures or their descendants will ever be able to do more than travel small regions of a single galaxy.
Great. And our next question is from Chang. Can you share what are some of the most exciting events or developments coming up in the next 10 years in astronomy, and what we can look forward to learning from these?
Sure, good question. Hard to predict, but 10 years is a reasonable time frame because we know the big projects and missions that are going to be out there within 10 years. You don't know what the discoveries they're going to make, but you can sort of guess the areas of interest. So I'll say the first innovation that will happen, this technical innovation for driving astronomy, is the James Webb Space Telescope. It's fairly, it's a mature project. It went way over budget, as I'm sure most of you know, but it is in its final stages of preparation for launch in a year and a half. And it's going to be the biggest telescope we've ever put in space by a long way. It's 6.5 meters compared to the 2.2 meters of the Hubble. So it's a lot more light gathering power. Far from the Earth, in a very dark place, able to observe in the infrared extremely well. So the James Webb is going to look at first light in the universe. So I think within a decade, with the James Webb, we'll have detected the very first galaxies forming in the universe, what's called first light, when the first gas clouds collapsed after the Big Bang, probably within 100 million years of the Big Bang, and we see those fireworks starting for the first time. That'll be extraordinary. I also think what possibly with the James Webb and possibly with ground-based methods, we will detect the first signatures, this is more speculative because it may take longer than 10 years, of life on another planet, another Earth-like world. And we'll do this by taking the feeble reflected light from an Earth-like planet, which of course is about 1 billionth of the light from the star nearby, the light that reflects off that Earth-like planet is 1 billion times fainter than the star. So you have to blot out the star, take that feeble reflected light, smear it into a spectrum, and look for what are called biomarkers, the spectral signatures of life, like oxygen, ozone, methane, water vapor. That experiment is just on the edge of being doable now, and we're starting to have bright enough or near enough Earth-like exoplanets to do that experiment. So a decade is about the time it might take for that to succeed, which would be an extraordinarily exciting occurrence. The third thing that should happen within a decade is that gravitational wave astronomy should take off. LIGO is going to enter its most sensitive phase of operation in about a year. And really, we'll know very quickly. It won't take a decade. We'll know within a year of LIGO operating in its full capacity whether gravity waves exist out in the universe for us to detect. LIGO is either going to see something happening with gravity waves pretty much every week, if not every day, or it's going to detect nothing, in which case back to the drawing board on gravity, either of which is actually an exciting outcome. So gravity waves are going to happen within the next decade. In the solar system, it's a little more tantalizing because the solar system exploration is so hard. We don't have any super ambitious Mars missions within a decade time frame. As you probably know, there's going to be a twin of the Curiosity rover with more capability and different instruments sent in 2020, so that's within the 10 years. And it will be more of a life-detecting rover than Curiosity is, but it still won't be able to dig deep enough into the soil to find layers that could have existing microbes. So I don't think we'll find actual life on Mars with the next Curiosity rover. And 10 years, unfortunately, is not the time frame within which we'll be able to bring back Mars rocks, sample return, nor send astronauts to Mars. So Mars exploration is going to take longer. We will have the Europa Clipper, so we will have the Ice Clipper, the mission to the outer solar system, which roughly in 10 years from now will start to arrive in the Jovian system and start to explore Europa, this incredible water world that orbits Jupiter. But that's not quite within the 10-year time frame to do that science. So I think that's my short list of things I think will happen.
Okay, and our next question is from Abhinav, and it's related to a different moon of Saturn. Recent discoveries about Saturn's moon Enceladus says that there certainly is a liquid ocean under the crust. Since water is thought to be a very important component for life, how do you imagine the type of life to be present there, if there should be life?
Right, it's a wonderful question because we'd love to know the answer. The Cassini mission, which has been multiply extended and has another 3, I think, or 4 years of life left, is going to continue to explore the Saturn system and is going to make as many flybys of Enceladus as it can. And it will do the trick that it's already done a couple of times of flying very close to Enceladus and sweeping its instruments through these geysers, these icy particle jets that come from the hot spots on Enceladus surface, sniffing what they contain, doing spectroscopy of them. We know it's salty water with some basic organic ingredients. We're not expecting microbes to be in those geysers, and the instruments on Cassini couldn't detect them even if there were. But as for the state of Enceladus, it's still a little uncertain because the best models suggest that indeed there must be liquid water, a reservoir, maybe not a huge one, it's a small moon, of liquid water, kept liquid mostly by pressure and by little tidal heating from the big planet itself, Saturn. So there is liquid water under a rocky, icy cap where through fissures in that icy rocky cap, these geysers appear, and it looks like hot spots to a thermal imagery. So that's a speculation. We have no idea how much water is liquid under the surface of Enceladus. It'd be great to know. It's depending on geological modeling, and we just don't know enough about the moon to say that. It would be wonderful if we could land something on Enceladus, and we actually have the technology to do so. We can land on a comet, and those technologies are quite mature. But again, it's very far away. It would take a decade or 7 years at least to get there, assuming you could design the mission, build it, and launch it. And nobody's got a funded plan to do so. So we're going to be left speculating about Enceladus for quite a while.
Okay. Our next question is from Gerald. Adaptive optics have been mentioned several times during the course. How would an image taken using adaptive optics compare in clarity to an image taken by a space-based telescope of the same object?
Um, until a couple of years ago, the space-based image would always have been better, because space it's not just that there's no atmosphere when you take an image from space. Also, the stability of the space environment. The temperature is essentially the same. The solar radiation is the same, depending on the orbit of the spacecraft. So it's extremely repeatable to take images from space. And so the Hubble Space Telescope's images, of course, are the archetype of super sharp images from space. But in the last couple of years, ground-based methods have really caught up completely with what you can do from space, with the extra advantage, of course, of the fact that you have bigger mirrors on the ground, and the diffraction limit, or the sharpest image you can make, scales with the size of the telescope, which is one of the reasons astronomers like larger telescopes. And since we have telescopes on the ground that are several times larger than Hubble, you, in principle, can get resolutions that are several times better than Hubble, mitigated by the fact that you have to correct for the atmospheric blurring with adaptive optics, and that was the hard trick that people have just perfected. But they've perfected it now to the point where last year, one of my colleagues, Larry Close, and I think I put the image of this into the course, one of my colleagues, Larry Close, professor doing infrared astronomy, he published the sharpest image ever taken from the ground, or the sharpest image ever taken of the sky, because his point was it was better than the same or the equivalent Hubble Space Telescope image of that same object. So basically the ground-based techniques with adaptive optics have caught up and even surpassed what you can do from space. So that's a dramatic piece of progress, because 5 years ago that simply wasn't the case.
Okay. Question from Dragos. It is generally accepted that the universe formed from a singularity following the Friedmann model. However, is it possible to consider, or was it ever considered, a situation where we had more than one singularity? Let's imagine a pre-universe collapsing, just like a star into a black hole, but not towards a singularity, but towards two or more, which then exploded into big bangs, triggered one because of the other. Is it possible to have something like this?
So let me pick apart two aspects of this question. It's a good question. It's also beyond the realm of conventional cosmology, because the Big Bang, as I mentioned earlier, only describes forward progress from an initially super hot, super dense state. As for the precursor state, this is the basis of the multiverse, the quantum fluctuation idea for the creation of our universe, with the possibility of other quantum fluctuations. For the business of expansion and recollapse, that came up with the idea of the oscillating universe, back when we didn't know whether the universe would expand forever or recollapse, before the discovery of dark energy, or the fact that there's not even enough dark matter to make the universe recollapse. We now know that the universe will expand forever and get bigger and bigger. But before that, we had to contemplate the idea of a recollapse and then a bounce, and maybe there's a set of cycles. And if that's not happening in our universe, maybe another universe next door is doing this cycling behavior. And that's still theoretically possible. So part of what you describe is possible. It is possible to have cyclic universes, in principle. Our universe does not appear to be such a cycling universe. It appears to have had an initial singularity, then an expansion, which is now an accelerating expansion, and that's the end of it. It's just going to continue to thin out forever, as far as we know. But other regions of space-time may have had something different going on. We don't think these different events would have had any communication between each other. They would have been independent of each other, in the sense that black holes in their event horizons seal them off from the other parts of the universe. So our observable universe is not intersecting or interacting with these other potential events. But there's a lot of speculation, and indeed there's some fairly sophisticated theoretical calculations of what the question was asking about, how that might happen. But they are, at the moment, untestable, so they're not a part of standard cosmology.
And our next question is from George. Would a hypothetical alien civilization living on a planet around a red dwarf star have their eyes evolved to see in the infrared regime?
Sure. No reason why not. Our visual apparatus, and remember that there's convergent evolution such that eyes, or something like eyes, have developed independently on the Earth in forms of life that are very different. Probably the best example is the octopus. So cephalopods separated from humans from the tree of life 3 or almost 400 million years ago. So they're really quite remotely related to us, and they live in a liquid environment in the shallow sea or the oceans where light can penetrate, and they evolved eyes too. And the eyes of the octopus and the eyes of humans and other mammals and fish and so on, they're all sensitive to roughly the same wavelengths of light. And the sensitivity of those eyes is very well matched to the solar spectrum, which is to say that it's matched to a star which is a G-type star with a surface temperature of about 5,700 or 5,800 Kelvin, putting out on average yellow light. So yes, biology has formed its most sensitive sensory apparatus, the eye, in a way that's neatly and completely well tuned to the energy output of our star. And we would imagine that if biology exists on other planets, around other types of stars, those life forms would have also adapted to utilize the energy or the radiation from their star. And if that star happens to be a red dwarf, there's very little visible light. The very coolest red dwarfs emit almost no visible light, just a feeble amount of red photons, and then most of the photons are in the thermal infrared. And yes, it's completely plausible that creatures on those planets would not have eyes the way we understand them, but would have infrared sensory equipment, which could involve a lens and so could be eye-like, but doesn't have to be. We know, for example, that some fish that live at the deeper elevations or the deeper levels of the ocean where light doesn't penetrate actually do see infrared radiation. We, of course, know that bats use sonar because they do their main foraging and eating in the dark when will be no light. And we know there's magnetic sensing that occurs in many parts of the tree of life. So other sensory modes are possible, and indeed, they should all be dependent somewhat on the properties of the star.
Our next question, and this is going to be our last question, it's from Gary, and he asks, dark matter still doesn't sound like a very elegant solution to me, but I found the multiple lines of evidence in the course to be compelling. Has anyone looked for a possible relationship between the physics of the active galaxy early stages that may be common to all galaxies and the distribution and nature of dark matter?
Yes, I mean, it's an interesting question. So, dark matter is a ubiquitous component of the universe. We found it, and it's more extended than normal matter. So part of the answer to your question is it doesn't relate very directly or tightly to active galaxies, to the supermassive black holes that power quasars and other active galaxies, because those black holes are extreme concentrations of matter. And dark matter is more loosely structured or clustered. The gravitational potential, if you like, is shallower than that of a normal galaxy, and certainly much shallower than the cusp of matter distribution where you find a black hole. So there doesn't seem to be any direct relationship between dark matter, as is found in all the galaxies in the universe we've measured so far, and the black holes that are formed at the center of galaxies. But they're dark in a different way. They're dark just because they fit the formal definition of a black hole. And indeed, some of the material that makes them up must be dark matter, as well as normal baryons like protons, neutrons, and electrons. But there doesn't seem to be any connecting research evidence between dark matter and black holes in the center of galaxies particularly. But you're right, to address the more general question, the dark matter is not a very elegant solution because we're having to postulate to explain the properties of galaxies we observe. We're postulating something that's invisible, something that's never been detected in the lab, that has properties that we have to infer very indirectly. And that's a pretty unsatisfactory situation to be in. But the experiments, mostly in deep mines, trying to detect the fundamental particles that remain the best candidates for dark matter, those experiments are in a mature state, and many people believe they will either succeed or fail within the next 5 years, with two possible outcomes. If they succeed in detecting a dark matter fundamental particle, the problem is solved. We have the answer. If they do not, then we're faced with the fact that our gravity theory may be wrong. That would be exciting to a lot of gravity theorists, dismaying to a lot of other people, but it would certainly make things interesting. So thank you all for your questions. Great questions this week, covering the whole subject, and we'll be doing this again in a couple of weeks. Thank you.